Hello, and thank you for watching this presentation. My name is George Amoriukai. I am the last author of the paper Neural Fuzzy Extractors, a secure way to use artificial neural networks for biometric user authentication. So the paper deals with how to do secure biometric authentication. And we know that secure biometric authentication can be done with fuzzy extractors, specifically a variation of fuzzy extractors, so that we avoid storing representative biometrics from each user. For example, a database of fingerprints where each user would have one or a few fingerprints stored. So we want to avoid that. So for that reason, we'd like to only store hashes, for example, of a representative user fingerprint. And such a mechanism would not allow an attacker to reproduce a biometric, would not allow him to authenticate as a legitimate user. An attacker with access to this to the system who could potentially look into the database if such a database were available. And so this is very similar to how passwords are handled. Passwords are not stored in a database, but rather only some salted hashes of the passwords are stored. The problem with secure fuzzy extractors is that they exhibit relatively low performance, and it turns out that score-based techniques do a lot better. And so what about neural network-based biometric authentication? Well, they don't store a database of representative biometrics, but rather they store a classifier. So there's got to be a classifier that's stored on the authentication server somewhere that will take the user's biometric and produce an answer whether this is the authentic user or not. And so if an attacker has access to this classifier, they could easily invert the classifier and produce an input that would then allow them to authenticate as a specific user. So the motivation for this paper is the question whether we can combine the performance of neural network-based biometric authentication with the security of fuzzy extractors. And to solve this issue, we first asked, well, why do fuzzy extractors exhibit bad performance when compared to other methods? And can we change something? Can we modify perhaps the input of the fuzzy extractors in order to avoid the performance degradation? And so first, we have to understand how fuzzy extractor works and fuzzy extractors work. And a fuzzy extractor is basically composed of a secure sketch and some hash function. And the secure sketch is technically a decoding mechanism, just like an error correction code that needs to be decoded. So in this figure on the left, you can see different shapes, different colors. Each shape represents a specific user. So you have an output space, perhaps of a neural network, a vector space where the representation for each user has a certain shape or color. And you can see, for example, that the blue triangles at the bottom right of the first figure represent a certain user, and they cluster together kind of like in a sphere, in a hypersphere, if you think in a high-dimensional vector space. And it turns out that in this scenario, most users' embeddings or representations in this vector space kind of cluster together in a nice hypersphere. And then what you do is you take the center of this hypersphere, say that's a representative of the user, and then you define a codebook on this entire space. And the decoding region of this codebook has to be pretty much the same as the same size as the sphere that encapsulates the legitimate user's biometric representations or embeddings. And so how the secure sketch works is that you choose randomly a code word from the codebook. So here the codebook is all the entire set of black dots, and each black dot has this decoding region around it. So that if we are presented with something that's inside a certain decoding region, that we decode it to the center of that region, to the closest code word. And so what we do is we choose a random code word, and for our purposes, we could simply take this representative and decode it and produce the code word in that manner, but that's not necessary. And so we calculate the distance factor between the representative and that code word, and we only store this distance factor. So it's secure this way because given only the distance vector, an attacker has no way of knowing to what code word this distance vector refers to, and so they cannot find the representative. So the attacker's entropy, if you want, is given by the number of code words that fit into the space. And so how do we recover this representative given another input biometric that's slightly different than that representative? And you can see here in the right-hand side figure, there's this blue triangle. That's a new biometric entry from the same user, and it happens to be within the decoding region around the representative. Of course, there's not a proper decoding region, so we take that input and we add the difference value. Well, yeah, we subtract the difference factor from it, and we obtain some other point, and that point we decode to the closest code word. So we recover the code word that we chose originally, and then we add the distance vector to that code word, and we recover the original representative, and then we can store the hash of that representative. And then every time the user inputs a new biometric, it should be close to that representative, so we can recover the representative, and then we can produce the hash, and we can authenticate with the hash. So that's how the secure sketch works. The problem, of course, is that decoding generally implies, especially in a continuous vector space, like say r to the power n, decoding implies usually spherical decoding regions. And that can pose a problem. Now, if the outputs of, if the embeddings of all the users and this vector space clustered nicely in spherical regions, that shouldn't be a problem. But in reality, that's usually not the case. In reality, you can have a situation like the bottom left figure, where you can see that the blue triangles and the orange pentagons, they're clearly clustering in distinct clusters. And you can think, well, yeah, it would be relatively easy to find the separation between these clusters, and neural networks are very good at doing that. But they're no longer amenable to spherical decoding regions. So that's the problem. How do we use decoding, which forces spherical decoding regions, with decoding regions that are highly non-regular, like the bottom right figure? We could technically take the embeddings of the users and process them further to cause them to cluster in distinct spheres. And that's how we do it. We actually take the artificial neural network and then we extend it, or we fit it with an expander. And this, the purpose of the expander is to take the say, decoding regions or the clusters shapes that occur naturally at the artificial neural network output, each cluster corresponding to a different user, and to push them into spherical, distinct spherical regions. And the output of the expander hopefully will have this property where all the users' embeddings will cluster nicely into distinct spheres. And if that's the case, then when we apply the secure sketch with the decoding mechanism that kind of uses these spherical regions, there will be no loss of performance because the embeddings already cluster in spheres. So this is the neural fuzzy extractor architecture. In addition to the expander, here we have the secure sketch and then the hash function, and of course, the comparison module. So how do we build the expander? Well, we want to build it using a neural network. And one way that we found that works for specifying the loss function is using a triplet loss that's associated usually with this Siamese neural network architecture. So we use a Siamese neural network training architecture in which we choose an anchor for each user, for example, an input biometric, which is called the anchor, and then we feed into one copy of the neural network, we feed that anchor, and then into another copy we feed a positive input, which is also another biometric from the same user, and then into another copy of the neural network we feed a negative input, which is a biometric from a different user. And the loss function is based on the output of all three neural networks, and it aims to decrease the distance between the outputs of the first two neural networks, which take the anchor and the positive, and to increase as much as possible the distance between the output of the neural network taking the anchor and the output of the neural network taking the negative example. So as depicted here on the right hand side, you can see that after learning, basically the distance between anchor and negative is supposed to increase, while the distance between anchor and positive is supposed to decrease. So that naturally turns out to kind of cluster user embeddings into distinct and spaced, as far away as possible, spheres. And so what about the secure sketch? What do we do for the secure sketch? Well, we do two things. First, for a baseline comparison, we use a distance-based decoder because we thought, well, if we're going to see some degradation, it could be because of two reasons. It could be a degradation because of the code itself that we use, or it could be a degradation because the expander doesn't do a good job forming spherical regions. And so we wanted to do a comparison. So we used a distance-based decoder. So this one requires representatives to be stored for each user. So clearly, it cannot function with our secure fuzzy extractor architecture because we would need to store representatives, so that kind of defeats the purpose. So the distance-based code is only for comparison purposes. So how this is going to work in reality, it's going to use a decoder, the decoder of a channel correction code. Among these codes are the low density lattice codes, or LDLC codes. There are other codes as well, like polar codes do pretty well getting close to capacity, but we only tried low density lattice codes. And so because they work pretty well, then they should do similarly to distance-based decoding. They should kind of form spherical decoding regions. And so the LDLC code, LDLCs, or the low density lattice codes, are defined by a parity check matrix that's sparse, hence the word low density. Our parity check matrix H is 128 by 128, so we use an expander with output of size 128. And then each row and each column consists of a bunch of zeros and a few elements, and we choose, there's several ways, there are several ways to choose these elements, but we chose them according to the original paper that introduces low density lattice codes. And we choose them as different versions of the set 1/2, 1/3, 1/5, 1/7, 1/11, 1/13, and so forth. So for example, we experimented with 3 and 5 weights, meaning that for d equal to 3, we only use the first 3 elements, so 1/231, 1/317, 1/511 in this case, and the rest of the elements of the columns and the rows are 0. So in each column and each row, there are exactly these 3 elements in different positions. So we tested the codes, and you can see here 2 diagrams showing the performance, and they do pretty similarly. In fact, it turns out that d equal to 3 kind of performs a little bit better. So we just went with d equal to 3. It's easier, and H is sparser. Now, the generated matrix of the code is this G, which is the inverse of the parity check matrix. So given a message, you represent the message as a vector of integers, and then let's call this vector b, and then the code is x equal to g times b. So now given a noisy version of x, say x prime, which in our case would correspond, x would correspond to the representative biometric, and x prime would be a new entry, a new biometric from the same user. So given a noisy version x prime of x, then you have to find a vector of integers, that's b prime, that's the most likely to have generated this version of x prime. And for our experiment, we used 2 fingerprint databases. We went with fingerprints. They're rather easy to process. The design can work very well, we believe, with any type of biometrics. And so we used 2 fingerprint databases, the FVG 2006 database, has about 150 fingers, 12 impressions per finger, and a PolyU database, which has pretty much double the number of fingers, but only 6 impressions per finger. We use 3 different classifier architectures that are pretty well established: VGG16, ResNet, 15, MobileNet, and then we concocted 4 experiments. We have a baseline classifier experiment, with a classifier trained in the Siamese network configuration, and then classifier trained in the Siamese network configuration, to which we add the expander, and we only train the expander, and then we take both the classifier and the expander, and we train them both simultaneously in the Siamese network configuration. The baseline classifier is just for baseline comparison. The classifier as it was originally designed, but of course adapted to the fingerprint databases. So we did learn the classifier on our databases, and then it turns out that our Siamese network configuration was achieving much better results. So we actually took the baseline classifier and trained it in the Siamese network configurations to make things fair, more fair, the comparisons more fair. And then clearly we expect that the last scenario, which trains the classifier and expander together, should perform the best. But it turns out it depends on the situation. And then the third one is the more realistic one, where you already have a trained classifier and just stick on the expander, and you only train the expander, so you're most interested in how that performs. And here are some of the results. We have plotted here the equal error rate and the area under the ROC curve. So just looking at the area under the ROC curve, we see that the baseline classifier usually does worse, and then this Siamese network trained classifier does quite a bit better. And it turns out that when you add the expander, the area under the ROC curve actually grows. Most of the time it grows. So there's no loss. It turns out there's no loss. And these tables also show you the difference between the distance-based decoding and the LDLC decoding. And it turns out, surprisingly to us, that LDLC decoding actually does better than distance decoding. And we believe that that's because distance-based decoding does not completely fill the vector space at 120 dimensions. So we think the code fills the space a bit better. So this is pretty much what we did at a very high level. Thank you for your attention, and I would strongly encourage you to read the paper and find out more details.